Hey, chemistry, how you doing? Ready for another flipped lecture? Isn't it amazing that you get two in 1 week? I know, who would have thought you would have been so blessed? But here you are. We're moving on to the next section when we talk about electron orbitals is being able to read the periodic table and predict the electron configuration of an atom based on its placement in the table. So the table is very useful, and if you didn't like that diagonal filling model, this will replace that for you. Okay, so let's jump into it. The periodic table arranges the elements in the periodic table according to their chemical and physical properties, and also according to the electron configurations, but we'll get to that in a minute. You've seen the periodic table before. This is something that you meet for the first time probably in late elementary, middle school sometime is probably the first time you've seen it. We dealt with it in physical science a couple years ago. So this is something that should be very familiar to you. And so as you look at it here, everything in a column shares some kind of chemical property. All of these react very strongly with water. All of these are very excited to grab one more electron and are very, very reactive. Things in this middle area hold their electrons loosely and can conduct electricity well, things of that nature, right? And the rows also have meaning, and we'll get to that too. So they're arranged according to mass, they're arranged according to atomic number, and they're arranged according to chemical and physical properties. So lots of reasons why they are in this particular arrangement. In each field, you will see that the element has been given a 1 or 2 letter abbreviation for its name, and that serves as the symbol for the element in compounds and in chemical reactions. Anytime we're referring to that element, we can just use that 1 or 2 letter symbol to represent that element. Sometimes it makes a lot of sense. H for hydrogen, that makes sense. C for carbon, O for oxygen. Sometimes it doesn't make sense. PB for lead, SN for tin. Some of those are weird, but the reason they're weird to you is because you don't speak Latin. Well, you're learning. I know. Actually, you juniors, you should speak Latin. No, it's okay. But these are, sometimes they're abbreviations from the English word. More often than not, they're the abbreviations from the Latin word that the element was named after. So sometimes it's just a language thing, but a lot of times it makes sense. When it doesn't, you'll just have to learn them. Sorry, Fe is iron. So there it is. But they have these symbols, 2 letters or 1 letter, depending on if something else also starts with that letter. And it's based on their Latin name. Sometimes it's the English, but usually it's the Latin. Okay. When you look at the field, if you blow it up a little bit there, the number above the element tells you how many protons there are. Not always how many electrons, although in a neutral atom where there is not a charge, then it's the same number. Beryllium, which is what I've zoomed in here on, beryllium has 4 protons. It always has 4 protons. If it doesn't have 4 protons, it's not beryllium. But it also has 4 electrons if it's not currently in a chemical bond, it's not been ionized, things of that nature. So 4 protons always, 4 electrons usually. Okay, and so that's the number there above the symbol. We arrange them in columns, as I've already said, which roughly coordinates with their physical and chemical properties. So things in the column tend to share characteristics. There are some groups that are kind of slanty and cockywampus, and they're colored there for you in the table, and you can see that. But for the most part, it's the columns where things tend to behave the same way, and that has to do with their electron configurations. The reason they behave that way is because of the electron configurations that they share with everything in that column. The columns also demonstrate the outermost valence shell. Now, valence, that word you should remember from physical science, but it's the outermost shell of electrons, the electrons that the world sees, that the atom has. And the periodic table demonstrates to you where that element finishes filling its electrons. Where is the outermost shell? So if it ends in an s orbital, then you'll find it in these 2 columns. Hydrogen, lithium, beryllium, magnesium, rubidium, barium, francium, all of these guys here, they all have an s orbital as their outermost energy level. Okay, the electrons over here, they have a p orbital as their outermost energy level. Now, the helium is kind of strange. He still has an s, but he kind of goes over here for electron orbitals, but because he's a noble gas, he gets to get moved over here. So helium kind of throws it off, but that's okay. All of these guys have a p orbital as their final electron shell. Okay, things in this area down here end in a d orbital. Okay, and then lastly, things down here end in an f orbital. So it's not that these ones don't have SPs and Ds, it's that the outermost energy level, the outermost shell, finishes in an F. Okay, and so S, P, D, F. That should help you as you read the table. Now, the rows are the electron shells, the energy levels. So we have in row 1, we have only energy level 1. In row 2, we have energy level 2. In row 3, we have energy level 3. In row 4, we start energy level 4, but it gets a little strange here. This is 3D. And then we go back to 4P. Now remember, that's how things get filled, right? Is they don't always fill 3 completely before it goes to 4. Remember the diagonal thing? So this shows you that as well. We're going to fill 4S, and then we're going to fill 3D, and then we're going to fill 4P. Okay? And then the same thing, 5S, 4D, 5P, 6S, and then here we go, 4F, 5D, 6P, 7S, 5F, 6D, 7P. Okay? And so the table steps down, and you can see that this actually goes in here. So the table would have step, step, step down, and then step up, step up, step up, step up. This part is just written down here so that the table can fit on a page nicely. Okay? So each time you go down a rung, you are going to the next energy level. So remember, this guy kind of belongs over here as far as this goes. These are P's, and then you step down, and the P's start at 2. See, the P's start at 2. And then you step down again, and these are the D's, and the D's start at 3. So even though he's 2 rows down, he actually, the S's start at 1, the P's start at 2, the D's start at 3, and then the F's start at 4. Even though it's 2 down, 2 down, it's only 1 and 1 as far as the energy levels go, right? So just remember that the counting is kind of shifted. But once you figure that out, then you can just read straight across the table to get how energy levels are arranged. So if I wanted to say, what's the electron configuration of silicon? I would say, well, it has 1 s orbitals, then it has 2 s orbitals, and then it has 2 p orbitals, and then it has 3 s, and then 2 p, and I end at 2p2, because there's 2 electrons left in 2p. Okay? If I want to do the same thing for lead, I could say it has 1s, it has 2s, it has 2p, it has 3s, it has 3p, it has 4s, it has 3d, and then 4p, and then 5s, and then 4d, 1, 2, 3, 4, 5, 6, 7, 8. Done. All you have to do is read across. It's a lot easier for me than the diagonals. All you have to do is remember that the step downs happen, step down, S's start at 1, P start at 2, 3D start at 3, F's start at 4. Okay? And if you put it all together again, I showed you a picture yesterday of a carnival balloon thing. This is another image of that. This is actually something that we derived in a lab, my first year teaching chemistry here at the school, and we're going to do the same thing. We're going to make that picture as well. So it's kind of cool. And you will see electron orbitals in all different arrangements, and hopefully that'll help you understand how all of this works. If you have any questions, let me know in the comments field below. I'll try to get to it before class. Otherwise, I'll see you in class tomorrow. God bless you. Have a wonderful evening.